Well, welcome everybody. Really appreciate you taking time out of your busy day to listen to our presentation. Like Bailey said, the topic for today is how embedded resistors can revolutionize high-frequency electronics. So again, I'm John Andresakis. I'm the Director of Business Development here at Quantic Ohmega Ticer. I'm a industry veteran with over 4 decades of experience in the printed circuit board industry, spending a lot of time working on design, building, and coming up with materials for making printed circuit boards. So today we're going to cover, what is, driving our modern communication networks? What are the trends? And where do embedded resistors fit into this trend? We'll talk about the technology of embedded resistors, share some applications, and then what we have up our sleeve, what's in development, what we're working on for the future, and then how to get started with embedded resistors. Then we'll have the summary and questions and answers. So we all know we live in a modern communication world where there's a growth of mobile technologies, not just for cell phones, but also for automobiles and other systems. And it's driving more demand for bandwidth. And with 5G, millimeter wave communications, and other applications, we're really pushing the boundaries of what can be done with existing technology. And so this really requires a lot of sophisticated antennas and sensors. One of those type of antennas is an actively electronic steered array, which is becoming increasingly popular for managing these high frequency and low power signals. As I think you all know that, as the frequencies have gone up to carry more bandwidth, more data, like 5G, it's much harder to have those signals transmit. And so we need to get more sophisticated in our antenna systems. So, where does embedded resistors fit into this technology? Now, the AESA technology has traditionally been used in defense applications because of its accuracy and because of what it can accomplish. And so, but we're seeing it more now being used in commercial applications, just driven by the need of 5G, networks. And, people are not familiar with these actively, steerable arrays. It can present some design challenges because now, as opposed to a passive array, a typical phased array, the active array has a lot more electronics. And because of that, they need a lot more passives to go along with the active components. So you get much tighter routing, high layer counts, and limited surface area of the PCB. So as a designer, what do? You're stuck basically having a lot of these resistors and other passive devices you have to put in order to accomplish the needs of these type of systems. And so we really need to do something to free up that board space. And so that's one of the things that we can do with embedded resistors. And not only do you get the benefit of freeing up real estate, but you also get improved high frequency performance, which I'll go to in a little bit. And also, everyone says, oh, resistors are cheap. Well, resistors for regular DC type, circuits or low, digital type circuits, yeah, they can be pennies or fraction of pennies depending on the application. But when you're getting into the very demanding requirements of high frequency resistors, now we're going from pennies to possibly dollars per resistor. So there could possibly also be a savings. So you can see now, resistors are growing and the passive devices are taking up much more room. So that's why we're looking at the technology of embedded resistors. So I mentioned that you save in real estate. So if you could take all those resistors off the surface of the board and put them down inside the board, you get that area savings. But what about performance? Well, here's an example where we took your typical 0402 surface mount resistor, and it's not just the resistor we're worried about. We also have to worry about the vias and also the connections, which is typically a solder joint. And so by doing, you look at the total of, you can get a really good SMT resistor, but by the time you put the vias and the traces and the solder all in place, you can start driving up your equivalent series inductance and also your capacitance. And so you can really, if you look at this particular application, your total could be 6.29 nanohenries. But if you go down now and you look at the embedded resistor, now you've eliminated the vias, the solder joints, and now the resistors in plane with the conductor. And so you can see that we can get an order of magnitude reduction in the inductive reactance. And like most things when it comes to frequency performance, as the frequencies get higher, this difference just gets much bigger. And so you can see that by the time we're just up to 5 gigahertz, we're already seeing that a major reduction in the inductive reactance, which really helps with electrical performance. So here's a depiction of what we're talking about with embedded resistors. They're basically thin layers of non-magnetic resistive materials and the deposit on copper foil, typically by sputtering or plating. And what's nice about this, it utilizes existing printed circuit board technology. So there's really not a major investment in order to implement this technology at the PCB shop. We need to test the inner layers electrically as well as the bare boards to make sure that the resistors meet requirements and that they meet the values as well as they're intact. And so if you could peel back the layer of a circuit board, you'd see the resistor layer underneath, and those little gray rectangles and squares kind of depict what a typical embedded resistor would look like. So getting a little bit more into the technology of the embedded resistor, how it's made. There used to be two companies, Ohmega Technologies and Ticer Technologies, and they were brought together under what we call Quantic Electronics umbrella back in 2021. So now both technologies are available from us, Quantic Ohmega Ticer. And so they're made in a wide web roll-to-roll format. And so they're very conducive to volume manufacturing. The thin metal alloy copper foil combination we like to refer to as RCM, which is resistor conductor material. So when you buy the material, you're getting both the resistor, onto the conductive copper. And it's basically laminated to any dielectric material of your choice, just like traditional copper foil. And then it's subtractively processed to basically produce the copper circuitry and the planar resistors. The difference between the two is that the Ohmega Ply RCM is actually electrodeposited non-magnetic nickel phosphorus. And it's the copper foil supply is out of Denkai America, which is in Camden, South Carolina. It's the used to be known as the Oak Mitsui plant, so that our majority of our copper foil is domestically supplied. But we do have some developmental foils out of Denkai, Japan, Circa Foils Luxembourg, and Mitsui out of Japan. And so we are always looking at alternative copper sources depending on our needs. The a direct customer is typically the copper-clad laminate supplier. So it'll be your Rogers, your AESA, Isola, and others. So it's basically whatever material the customer requires, we would then sell to the laminators. And then we have a 21,000 square foot facility in Culver City, California, which is not that far from LAX. Our other facility, another company, is the Ticer, and that has a proprietary sputtered non-magnetic nickel chrome. We also have nickel chrome aluminum silicate and chrome silicate oxide. And these two other alloys have higher resistivity so that we can make higher resistance values. But over 90% of what we produce is the nickel chrome. The again, copper foil supply is very similar. We have Denkai America as the largest supplier, but we also get a low-profile copper foil out of Taiwan Copper Foil. Again, we're working with the same development projects on copper foils from Japan, Luxembourg, and also from Mitsui, Japan. And then we're also work with the major same CCL laminators, except in some cases we've added, Panasonic and DuPont has been doing work with Ticer for a long time, and so some customers prefer that material on those particular substrates. But again, we can supply pretty much any material on any substrate. We have a 14,000 square foot manufacturing space that's split between our Windsor, Connecticut facility where the sputtering occurs, and then our finishing operation is in Chandler, Arizona, in the Phoenix area. So to get into the process, it basically is, like I said, traditional printed circuit board process. We start with the inner layer, like an inner layer core, and we put the photoresist on. We expose it, the pattern, we develop, and then we go ahead and we etch the copper where we don't want it. So basically, we're still protecting both the resistor and copper at this point. Now, in the case of Ohmega, there's still a residual resistor layer that has to be removed because the copper chloride doesn't completely remove all the resistor material. So we go through a copper sulfate bath, maybe 10-15 minutes, and all the background resistor material is removed. In the case of the Ticer material, it's so thin and it's a nickel chrome that the copper sulfate the copper chloride typically takes all of the background resistor material away. So you can skip that additional step. Then after the resistor material, the background resistor material is removed, we strip the photoresist and we start the process again. Put the photoresist down, but now when we expose it, we open up the window where we want the resistor to be. Okay, and then we'll go through an alkaline etch. And that's the beauty of this system is the alkaline etch, which is typically your outer layer etching solution for most circuit board shops, will remove the copper selectively, but not touch the resistor material. And so once that's done, we will strip off the photoresist, and now we have the resistors exposed, and our patterns are done. And then you would go your traditional circuit board processing. First you do your electrical test, then you would do your oxide process or oxide alternative, and then go into your lamination process and go from there. So from that point on, it's like a traditional circuit board operation. So what do we mean by ohms per square? Okay, ohms per square watt. Well, it's a sheet resistivity, and it's a dimensionless unit. And so basically is if you have a square of material, like this example would be 25 ohms per square, what would happen is that whether it's 1 millimeter by 1 millimeter or 1 kilometer by 1 kilometer, it still would be 25 ohms. Okay, the only difference would be in the power handling capability. The way you make resistors with this is that it's basically the ratio of the length to width. And so example here is if you have a 25 ohm per square material, if the length is twice the width, you're going to get a 50 ohm resistor. And if it was 4 times, you get a 100 ohm resistor. So by controlling the length to width, and once a sheet resistivity is picked, you can make different size resistors. And we have an example of that on the right side. So with a 100 ohm material, we were able to make everything from a 50 ohm, which now the width is twice the length, to up to 100, up to 10,000 ohm, and that's quite a range of resistors. That's why most people typically only need one layer of this material inside their circuit board to do what they're required to do. And you could see here that it's kind of a serpentine pattern to make these very high resistor values. So it takes up very little area. You can make a large resistor by just serpentining it. Now, one thing we like to guide people is to try to make the largest resistor that they have room for, because smaller resistors will have higher tolerancing because of the fact that the etch factor that the board shops can hold, maybe, most board shops can hold plus or minus 12.5 microns, half a mil. And so again, as it gets smaller, resistors get smaller, that etching tolerance will have a bigger impact. So again, you try to make it as big as possible. It also help with power handling as well. We have sheet resistance values between 10 and 1,000 ohms per square. And the way that's controlled is by the alloy and also by the thickness. So the nickel phosphorus is the thicker material, and it can go to the 10 ohms. And the chrome silicon oxide is the material we use for the 1,000 ohm. Most of our customers will find that working in the 25, 50, and 100 ohm per square is this kind of the sweet spot where a lot of designs seem to fit in. So talking about applications now, I mentioned the AESA radar and any other type of phased array. I'm using this kind of as a proxy for high frequency electronics, but we have a long history of this of our RCM material in RF and microwave circuits, operating up to 550 gigahertz and beyond. And most of them have been used by major defense OEMs. And again, they've been doing it for a long time. And what's nice about that is that anybody who's worked with defense, they really put materials through the paces. They check reliability, they check everything to make sure that it meets their, and they're usually very demanding applications. It could be space, it could be avionics, it can be a lot of different things that are under harsh environments. And so they by having the military as a major account, it's really gives confidence in the material. And also the material is very stable over frequency, time, and temperature. We've tested it from minus 55 to 125 degrees C, and typically the temperature coefficient of resistance is less than, typically less than a couple hundred parts per million. So it really doesn't vary much over the typical normal operating range of temperatures. And as I mentioned earlier, reduce the parasitic inductance and capacitance you have, now total fewer solder joints. Again, if you're going to be putting something and something that's moving or anything that is going to have any sort of vibration, solder joints are always typically a concern. And so, again, we can get rid of them, as well as the associated vias, which allow you, again, to get better packaging density and better, smaller form factor. So you can take up less room with your electronics. In the pictures below, you could see, we have, on the left side, we have a satellite application. On the right side, we got that phased array antenna. But in the middle, we got 3 examples that customers have shared with us of their like power dividers, which is a very typical application for these type of electronics. So again, if you didn't have our material in this application, you would now have to solder a resistor over each one of those gaps in order for the power divider to work. And so again, you're basically now taking something that could be planar in our case and putting a 3-dimensional device on top of it. No matter how small it is, it's still going to be 3-dimensional. So now if you want to bury it inside the circuit board, you'd have to go ahead and build a cavity into your prepreg and basically laminate that thing in, which could cause some problems. And so it's a much more elegant solution, especially for these type of devices. And this is where we see it has been used for years and a continuing interest. And as frequencies are getting higher, there's more and more demand for these type of applications. Another thing too in the communications world is that the material is also a absorber of electromagnetic radiation, and so it's been used in R cards, high impedance surfaces and frequency selective surfaces. An example here is from Toyon. We were glad they shared this with us, and it shows that by putting the R cards in there, they were able to cut out the interference and the noise outside of the frequency band they were interested in. And you could see that they had a really positive effect on the E-plane of the side lobes without really having any impact on the H-plane. So they got much better signal noise ratio and much better performance at putting the R cards in. And what's nice is by patterning the R card or your absorber, you can basically go ahead and tune what frequencies you want to reject, which ones you want to pass through. And again, it's a very nice solution for these type of applications. Now, somewhat related to high speed and high frequency is the fact that electronics is getting faster, and so we want to have the passive devices as close to the active devices as possible. And so we're now seeing applications where people would want to using our material as like termination resistors. And so you can look at these packages such as interposers, probe cards, or substrate-like PCBs, and you can now take that. The resistors are small, but the vias still take up space. And so if you can get rid of that, you can have, again, that improved electrical performance, get rid of the vias and solder joints. And it can also be used on rigid flex as well as rigid applications. What's nice about this material is you can use it as a flexible substrate, and we have a lot of reliability data saying that it will withstand multiple flexures over time. And again, you can now place your resistors wherever you have space, so you don't have to worry about about via placement. You can just put it inside your package wherever it needs to be. And again, signal integrity, especially as frequencies goes up, this is a very low data rate. It's only 1 gigabit per second, and yet you could still see the improved eye diagram, the signal integrity improvement. This was courtesy of applied laser technology. And again, it's because you're getting rid of that whole loop of getting up, through the solder joint to the resistor, back down, and so you get much better electrical performance. So not only is it good for high frequency, it's also good for high data rate, for high speed. The other place is that where we see a lot of use of this material is for the most advanced smartphones. And what's in those smartphones, these MEMS microphones. Many years ago, we started switching from ECM or the condenser mics to these MEMS microphones. And so the MEMS microphones consist of a silicon oscillator, basically takes the vibrational energy, and then it gets converted with an ASIC into the electrical energy, and then it goes and provides the output. Well, what happens is, because of all of the various frequencies that cell phones have to deal with, you have Bluetooth, you have your Wi-Fi, 3G not so much anymore, but you have 4G and 5G. All this thing is going on inside the cell phone. So you have to make sure that that the mic doesn't cause interference with those signals and vice versa. And by putting an RC filter inside this package, you can basically help eliminate that and get much better better signal integrity and much better output from the microphone. And the RC filter is accomplished by using our material, the resistor material, and also using an embedded capacitor material from my old company, FaradFlex. So the combination of the two makes for a really excellent RC filter that sits right in the package underneath the MEMS and the ASIC. And so the only thing in that cavity now is just those two devices, and no passes are required. And we see that this should be a technology that we see growing in other types of MEMS devices for the same type of reason of miniaturization, electrical performance. One thing, just as a side note, is because we're talking about things that could be up in space or on other planets, and they've been used successfully as heater circuits. I tell people our material can be used as a resistor, a heater, and if you give it too much power, it can be a fuse. So hopefully most people won't try to push it to that point. But the heaters are very, very good application of this material because they are usually smaller and need less power. If you just simply thin down a copper coil, using copper traces and make them thin to heat up. You can also avoid the use of some exotic resistor foils like copper nickel and others that are a little bit harder to process and could cause processing issues in the PCB shop. So since they already are using our material for resistors, it's basically a form of resistor that they can do. And it can be, again, both in rigid and flex applications. A couple of examples here. One is the old Beagle 2 rover that was on Mars, and they needed a heater circuit for their X-ray spectrometer. And it actually was able to heat it up to at least minus 50 degrees Celsius so we could work. In electronics, we almost seem to be worrying about getting rid of heat. Well, in some cases, like these hostile environments, you have to apply heat. So on other planets up in space, when things get cold, you need to have a heater source, and our material is an excellent source of that. Here on Earth, we're seeing a lot of it in the biomedical area. Here's an example of a heater that needed to go to 60 degrees C for a DNA sequencing piece of equipment. And the PCB, layer 2 of a 4-layer PCB was the heater, and it was designed for 50 ohm, 10 watt, 12 volt, and it did an excellent job with our 10 ohms per square, which is our thickest Ohmega material, did an excellent job as a heater. And we're seeing more and more medical applications of that. So as we talk about high frequency, anybody who's been dealing with both high speed and high frequency in our industry knows that the copper foils become under a lot of scrutiny. The laminate suppliers have done an excellent job working on various resin systems to improve the dielectric loss and improve the dielectric constant. But as you start getting into higher frequencies, especially as you start going over 20 gigahertz, the copper foil makes an impact as well. And so a major impact. And so we've been working on improving the roughness of the copper foils that we offer to our customers. Now, we get the copper foil from the major manufacturers, and we put our resistive material, which is so thin that it really doesn't change the topography of the copper foil. So whatever copper foil roughness we get pretty much goes on to the laminate customer with the same type of roughness. So when we started out Ohmegaply, the PT copper was very typical. It's still used a lot today, especially on things that are not operating at high frequency or maybe hard to bond to, but it's a roughness of 6.4. So it's kind of a traditional, printed circuit board copper foil that's been used for decades. But there was a need for lower profile, and that's when we came up with the TOC, and that is a lower profile yet, and that's available both on Ohmegaply and the TCR from the TCR Ticer material. And that one's a little bit better performance. And then it turns out that the Ticer people had worked on the EHF, which is the very low profile copper that comes from Taiwan copper foils. But even that, we think that it's an excellent product, but even that we want to push further because people are asking us for these really high frequencies. And so now we're working on a product called EPS, which is out of Denkai, Japan. And you can see now we're getting below 1 micron RZ. And that is currently in development. And so it was really designed originally for flex substrates, but it's now being used for rigid as well. And so Rogers has a lot of experience with high frequency performance, and so and they've been a good partner of ours for years. And so now we've been working with them on evaluating this foil. And when we want to check the performance of copper foils, we like to use an LCP product because that one is one of the lowest loss types of materials on the market. And so that way we can kind of take out the impact of the dielectric and have it more concentrated on the copper foil. So we used the 4 mil LCP, and you could see here, so we took the raw EPS foil. That was the foil as delivered from Denkai. We didn't put a resistor on it, and that's our control. And then we put both our 25 and 50 ohm material on it. This is the Ohmega ply. And then we also compared it against the standard copper that is used for this material, which is typically a rolled annealed. And then we also compared it to our TOC grade. And as you can see, in this case, the higher the line is on the chart, the better it is. It's less lossy. And so the raw EPS had really good loss characteristics, less than close to about 0.9 decibels per inch at 40 gigahertz. And then we're adding the resistor layers only incrementally change the overall loss performance, which is what you expect. The resistors are a little bit more lossy than copper foil, but it wasn't a pronounced difference. In fact, the biggest difference is really the copper roughness. And so, that's the main driver of the loss is the actual copper roughness and not necessarily the addition of the resistor layer. We did some resistance measurements. Of course, there are various PTFE substrates, and we did see a slight increase over FR4, which is very typical because of the higher temperature to laminate them. But the peel strengths were very good. And these, we didn't get as good of a peel strength on the flex. Some recent data says we're getting about 2 pounds peel, and we're still working on that. And so when it comes to being on thermoplastic materials like PTFE, we feel really good about the product. The issue is a lot of people want to use it on thermosets that are based on PPE, PPO, and so those are notoriously hard to bond to. So what we're working on now is bond promoters so that we can now utilize this foil on other substrates, and we're working with some laminators on that. So how do you get started? Basically, when you look at your layout, your schematic, you should be able to pick out which resistors that you really want to embed. These could be due to where they're placed, what their values are, and so you go look at your net list. You say, okay, these are the resistors I want to bury, and then you pick your dielectric based on your requirements, and then you'd look at the foil offerings. Now, the resistor selection, you should really look at the tolerancing that you want. If you really need a very tight tolerance resistor, then this technology will not give a plus or minus 1%. It's typically more in the 15-20%. But it turns out in reality, just because you can buy a plus or minus 1% resistor doesn't mean you need it. If you really do need it for electrical, you do all your simulations, and it says you need a plus or minus 1%, then you use a traditional surface mount. But if you don't need that, we think that the gains you get by getting rid of all that inductive reactance, and other types of frequency response, you'll be better off still burying the resistor. And you pick the foil, it'd be the Mega Ply or the Ticer, depending on what resistor value you need or what printed circuit board shop you're going to and which one they prefer. And then we have a list of simulation parameters that we give out to people so you can do your modeling. Most people these days will simulate their circuits way before building them. It's expensive to build and rebuild, so we help with the simulation of the performance you're going to get using the material. And then things to consider is that there are ohmic value shifts, and that typically occurs when you're dealing with the high temperature laminates like PTFE or flex polyimide, where the lamination temperatures are very high. So you'll get typically a characteristic shift. The Ohmega ply is a little bit more sensitive to that than the Ticer because of the nature of the material. But the nice thing about it is it's predictable and it's repeatable. So an example is if you have a 50 ohm material and it's going on PTFE, it might go to 55 to 60, but it'll always be the same, so that when you're designing your artwork, you'll now can design your artwork, assuming that you're going to get a 55 or a 60 ohm resistor to help you with centering the distribution of your resistors. The PCB process contribution, most of these people who deal with this on a regular basis know exactly how to process it to avoid any sort of processing issues. So there really isn't usually a lot. The biggest contribution you're going to get from the board shop is the tolerances, both for the etching tolerance as well as registration tolerance. Because if the registration isn't proper, you could get the resistors offset from the conductors, and you can actually get a total different resistance value. So it's important that the tolerances of the fabrication process are put into play. Also, power rating is important. We have a calculator available for both the Ticer and the Ohmega material, where you would put in the size of a resistor, the sheet resistivity, and then I'll tell you how much power you can handle for those resistors. Typically, most of the resistors only need to handle milliwatts type of power, and that's what typically they support. The thing is, our calculators are very conservative because it's basically done by testing the resistors in air, as well as there's only basically it's a double-sided laminate with nothing on the back side. So you really are giving it a worst case scenario, and then we derate it on top of that. Normally, when the resistor is buried, you have thermal mass around it, which will help absorb some of that heat. So people have typically told us, said, you told me it's only going to be 100 milliwatts, but I'm running up around 400 milliwatts with no problem. So again, it all depends on the stack up, and you can do thermal modeling to verify that. We have design guidelines available as well, so that so that you have things to consider when you're laying out your circuits, how to actually do laying out of the circuit. Because basically you're not adding another layer to the board, you're just adding another artwork layer that has to be accounted for that second etch. And that's pretty much the biggest part of dealing with the design software. And we have a fabricator list available. We have many fabricators across the country and across the world that do this on a daily basis, from both prototype all the way up to full volume production. Last year, we launched a new website which combines both the Quantic Ohmega and the Quantic Ticer brands together. It's called quanticohmega.com, and it has both products there. We have a technical library which has a wealth of information. You just need to register once, and then you have full access to it. So it gives more product information. It gives you those design tools I mentioned, processing information for the board shops, in case there's any questions. We have a lot of articles there. And one thing I mentioned earlier is that a lot of our customers use our technology, but they don't always share the information because it's kind of a competitive advantage, or it could even be secretive based on the military type of application. And so, but academia is very good at taking our material, making it into different types of products, and sharing the data. So we have these are just three of the top articles in how our material has been used for phased arrays and power dividers. And so I think that there's at least a dozen or so more just on these type of applications, and then other applications as well. So I really recommend everyone signing up for the library. It only takes usually approval process takes less than a day to get you into the library. So in summary, the RCM foils have been used for decades in mission critical applications. They've been really put through the paces. We have a lot of reliability data in a lot of harsh environments. That's the beauty about being embedded, because typically anything that is going to destroy our material is going to destroy the circuit board first. So again, it's a very robust solution, a very eloquent solution to take care of your problems. Because I know that as designers, we're being asked more and more each day to basically put more things in a smaller space and to get things done very very effectively with the least amount of turnaround time. Also worry about EMI. So there's a number of issues that this type of technology can address to make your life easier. And so again, it enables very high frequency and high speed performance, and it is truly a blank slate. It's really you can really unleash your creativity. You're not stuck with having to use little rectangular features that you have to place somewhere. You can make all sorts of very interesting designs. We've seen people make very interesting designs, anywhere from, you can make circular resistors, you can make arc resistors. There's a whole bunch of things you can do that you couldn't do with a discrete component. And we're your partner every step of the way. So if you have an idea for a project, or if you're running into a problem, always feel free to contact us. You can contact us through the website, or you can call me or get hold of me directly at John Andresakis at quanticticer.com. And so with that, I really like to thank everybody for your attention. And one last thing I'd like to talk about is that we are going to be presenting a paper at the International Microwave Show this June in Washington, D.C. It's the last session on Tuesday, and we had built some RF attenuators in conjunction with our sister company called X Microwave. One of the nice things of being part of the Quantic group is that we have another dozen or so companies that deal with a lot of very mission critical components, and X Microwave is one of them. And so we worked with them with a design company. We built this attenuator, and so we've tested it up to 60 gigahertz and got excellent results. I wish I could share more results now. In fact, that'll be a topic of a future presentation, but we're kind of locked in that we can't talk much about it until after the IMS show by their rules. So once that IMS show is over, we'll be able to share a little bit more information. But if you happen to be at IMS, please stop by our booth as well as attend the presentation. And so with that, I'd like to turn it over to Bailey for the question and answer session.
We do have a couple here for you, John. First one is, how many PCB shops can process the resistor foils?
We have to date probably over 70 board shops across the world that can process the material. Again, we have a majority here in the U.S., but we have quite a few in Asia as well as Europe. So we typically, if a customer comes to us with their approved board shop list, generally we can find at least one shop that's on their list that they could utilize. And if not, we can work with them to either get a shop that they have approved to use our material, or get them a new shop that uses our material on a regular basis and get it on their qualified list.
Next question is, can resistors be on the outer layer of the PCB?
Yes, I mean, there are cases, obviously there's a benefit of being on the inside, being, additionally protected, but it can be used on the outside. The only thing is you typically would want to protect it just like you would anything with a solder mask. So as long as it has a solder mask on it, it should be fine. So, but we do, most people do have a tendency to use it on the inside, but there's no reason why it couldn't be used on the outside. It just needs additional extra care and processing during the outer layer process until the solder mask is applied.
Okay. What are typical tolerances for the material and the finished resistors?
Okay, the typical tolerances range from about on the material itself, about plus or minus 5%. Some of the other materials a little bit wider range. When get down to some of the thinner materials, may approach plus or minus 7%. But then it depends on the size of the resistor. So if the resistor is big enough, you can count on holding about plus or minus 15%. Some of the tinier resistors, might start creeping up into the 20-25%. But lots of times we're seeing people hold with good practices, somewhere in the 15 to 20% type of numbers.
Okay. Can anything be done to improve the tolerance?
Yes, well, laser trimming is available. It is, basically what you would do is you would basically, let's say you want a 50 ohm resistor and you want it to be plus or minus 1%. Typically, in reality, you could probably hold better, plus or minus 2% would be closer. Let's say you want to get down into that range, this low single digit tolerance. You would make your resistor, let's say, 47 ohms. You would design it specifically to be low, and then you would go ahead and do a laser cut into the resistor. So you'd measure it, laser cut, measure it, and then maybe I need to make another laser cut to get it to your tolerance. It's a very time-consuming process. Can be somewhat expensive, but again, if you need that precision, it can be done. We have a couple of customers now that are looking into that because actually they want to tune their circuits. So it's not the matter of that they want to trim the resistor just to trim the resistor's sake, but they're actually using it to help tune a circuit. And so that's an application where they're going to be doing the trimming anyway. So it didn't add to their overall process. But again, most people find that they don't really need to get that fine of a tolerance for the resistors.
Okay, here's another one. Ohmega and Ticer appear to occupy the same technology space. Will these products ever be rationalized to only one choice?
No. If you look at it, yes, there's some overlap in product capabilities, but there are some differences, and some people have preferences. And again, in some cases, the people have preferred the Ohmega material. They've been using it for years, and it's worked well for them. In some cases, they've used the Ticer. So they are complementary. They have, again, when it comes to the low ohmic values, like the 10 ohm, we only have the Ohmega available. When you start getting into the really high ohmic values, we only have the Ticer available. In that center spot, they do overlap, but we find that people have a preference one way or the other based on either AESA processing or power handling. So we don't have any plans to discontinue any product line or rationalize. We're going to be keeping both products alive and well for the foreseeable future.
Is there copper weight available? Or
Oh,
is the
yes.
copper weight available? Yep.
Yeah, so most of our copper is half-ounce copper because, especially with these type of applications, half-ounce copper or 18-micron copper is typically what most people want. But we have 12-micron copper and 1-ounce copper are available as well. So sometimes you may want a little more, copper there. So we have the 1 ounce. So again, they are available. We are working on some other alternative ultra thin coppers, which I'd like to talk to at a later date, which is really more designed for chip packaging. So in a future event, we'll be talking more about that product. But again, from a daily basis, 9.5 ounces seems to be always pretty much on the shelf. And then we also have the 1 ounce and the 35 micron and the 12 micron available as well.
Great. Thanks, John.